So I want to talk about the spring force and the normal force. Both of these are going to pop up and again. So let's first of all talk about the spring force. The spring force. Okay, so imagine a massless spring hanging vertically, and imagine what happens if we put a certain mass on it. So let's put let's say we put 100 grams on it. So what that's going to do is it's going to stretch the spring down. There's 100 grams, a certain amount. Okay, so I'm going to measure the amount of stretch. I'm going to call that delta y. All right, now what would happen if I put 200 grams on there? Well, if it's an ideal spring, 200 grams will weigh twice as much as 100 grams, and the spring will stretch twice as much. And so if I just show that conceptually here, okay, so there's 200 grams. And if this is delta y, this the displacement downward is, well, let's do it this way. 2 times delta y. Twice the mass, twice the weight, twice the displacement. And so the spring force, it's an interesting force. If we have a mass hanging on a spring and it's in equilibrium. Okay, now equilibrium, let's say this is m. This idea of equilibrium is a very important one, and it means what essentially it means is that F net is equal to 0 newtons. Okay, so here is the spring. We're going to characterize the spring with what's known as a spring constant. Usually it's written as K. The units for K. I'll often use this as meaning units of are newtons per meter. So if I did a force diagram for M, here's what it would look like. There is a downward force of the Earth on M, which is equal to m times g. That's a non-contact force. And m is in equilibrium, so there's an equal and upward force of the spring on m, and that force is equal to K times y. Okay, so K is characteristic of the spring. A stiffer spring would have a bigger value of K. A less stiff spring would have a smaller value of K. Y is the displacement that the spring undergoes. And so since the spring is being pulled down this way, since the spring is being pulled down this way, the force the spring exerts is opposite to its displacement. It's upwards. And so for that reason, the spring force, F sub s, is properly written as minus K times y. So in other words, the force that the spring exerts is proportional to a spring constant. It's proportional to the displacement. If it's in the vertical direction, typically I'll use y. If it's in a horizontal direction, I'll typically use x. And this negative here means that the displacement direction of the spring is opposite the force that the spring exerts. That's the spring force. Now we can actually use the spring force to measure weight. That's the simple scales that you see in the supermarket are examples of that. And if we can measure weight, if we're in a gravitational field and we can measure weight, we can also measure mass. Remember the force table lab where we took W is equal to mg, and if you know W and you know what g is, 9.8 meters per second, you can then deduce what m is. So that's the spring force. Okay, now let's talk about the normal force. Turns out that they're somewhat similar. That's not at all obvious. So if I have a mass m, let's say it's a block like this, and it's sitting on a table, what literally happens is the table will minutely distort. Imagine that it was on a rubber membrane, and the rubber membrane was pushed down because of the force of the Earth on this mass m. Well, that's what happens actually when m is put on any kind of surface. If it's put on a table, if it's put on a book, anything solid, there has to be a mechanism for forces being supplied. And so this surface, here's the important idea. This surface, I'm going to draw a line across here. I can change my color. So this is this red line represents the undistorted surface, and this green line represents the surface being pushed down. And so we can see that the surface is being pushed down by some y there. It's a displacement downwards, and so the surface is going to behave like a spring. It's just as if there's a big spring right here that's now being squished down by m. And so if this spring is being squished down, it's going to push up. So if we draw a free body diagram, a force diagram for m, it's going to look like this. It's going to look like a downward weight of force of the Earth on little m, which we know is mg, and it's going to be an upward force, which we're going to call this the normal force. The normal force of, let's say this is a table, the table on m. And the origin, the physical origin of this force is the distortion of that surface. And as we talked in a previous lecture, the word normal in this context means perpendicular to.